All right, this will be our summary of subelement T9, summary and commentary, antennas and feed lines, and we'll use our key takeaway slides as our guide. I made a little adjustment on the bottom section there and brought it into view a little bit. So from T9A, our key takeaways were beam antennas concentrate signals in one direction, and Yagis offer the greatest gain among common types. So yeah, I've actually got a couple Yagi antennas that I run on 2 meter and 70 centimeter. The neat design of these things is the elements for the 2 meter and 70 centimeter on the same boom on opposite sides or one over top of the other, depending on how you polarize it. You can have one common feed point on those, but I have them separated. But the gist of it is that it's a 3-element Yagi. And so you have the driven element, the reflector, and the director. The driven element, of course, is the antenna. It has to be is the resonant portion of the antenna. If it were, it's almost like a dipole design on a Yagi. It's two lengths of antenna that make up a resonant wavelength, and the signal comes out of that. It hits the reflector, which is behind it, and then is directed forward by the smaller elements going forward. The reflector is going to be bigger than the driven element or the resonant element, and then the directors are going to be smaller, and they will get smaller. If you have multiples, they'll get smaller than each other. You can have however many you want until you run out of space to make them. You can make that boom as long as you want to, and that will put more concentrated power in one direction, but it makes it a very narrow direction the further you go, which may be a good thing depending on what you're trying to do. I know some of the satellite operations, they have a few more director elements on them in order to kind of pinpoint, because you're pointing directly at the satellite, so you're going to concentrate more power right directly at it, whereas you may not want it to be as narrow if you're working single sideband or some local stuff. You don't want to pin yourself down to having to pinpoint that directly on it, but you want to be in that general direction. One of the advantages, like I have a hex beam, and it's kind of a 2-element setup, so it is very broad. It's about, I think about 70 wide, something like that on the azimuth scale. And so you can pretty much with it does direct power in one direction like it's supposed to, but that direction is very wide. So a lot of times what I'll do is if I'm working like FT8 or just calling CQ or something like that, I'll hit north, and then I'll go to northeast, and then I'll go to east, and then I'll go to southeast, and I'll go through each one of those, calling and getting various signals whenever I do that. Antenna polarization is defined by the orientation of the electric field, and you match polarizations between stations for best signals. So depending on what type of signal, like FM, you would have a vertical polarized antenna, and sideband you would have a horizontally polarized antenna. Especially when you're talking about beams, you can turn those either way depending on what you're using them for. Now, on your HF frequencies, though, you can also, depending on what you're trying to do as far as the polarization, if you're trying to just work stateside, something like that, then you may have more of an advantage with a dipole or something that is horizontally polarized. If you're trying to work DX, I use inverted L antennas, so a section of those antennas are vertically polarized, then they go up, bend, and go horizontal, but that vertical polarization gives you a better takeoff angle as far as working DX. And then shorter antenna equals higher resonant frequency, so the formula for dipole length is 468 divided by the frequency in megahertz. So if you're making yourself a dipole, and I actually did this for a 2 meter frequency for a repeater. I did a suction cup dipole I read about in one of the ham radio books, and you suction cup it to a window of a car, or on my case, I put it on the my house window outside, and to get the length of that dipole, I just took the local frequency the repeater that I was using, the transmit frequency. It was 146,040, so I just took that and divided by 468 and gave me the length in feet of what my antenna would be. And this is more commonly used in HF, especially making wire antennas, but it's a simple formula if you want to figure out what length of wire that you can that you need to have a resonant antenna for a particular frequency. Just keep in mind too, though, if you are making a dipole or an inverted L or something, you're using that formula to make an antenna for a particular band, that if you want to be able to work that entire band or have a shot at it, then get to the center of that band and make the antenna. Now, 80 meters is so wide that you will, if you do the center, you're going to compromise both directions. So if you have the space to do it, it would probably benefit you to put up a couple antennas for that band and work off of kind of each end of it. It used to be, in the olden days, we call it the 80-meter band, the 75-meter band, and it still technically is, but I think FCC terminology or study terminology, they just kind of shorten it and call it the 80-meter band. But that's something that that I actually have kind of a setup for, is I can go to one antenna that will tune better on the upper, the single sideband portion of the band, and then my inverted L that I have is cut for the digital end because I like to do CW and FT8. And so it's on the lower frequencies. Antenna gain redirects power toward a specific direction, and it does not create additional power. So yeah, when you hear speaking of gain on an antenna, it's just a redirecting of existing power. You can't really create additional power with an antenna. You can just concentrate what you have. So if you're running a 100 watts on 2 meters, then you can either have 100 watts trying to go in all different directions and not really have an advantage over one or the other, or you can direct more of that 100 watts in a certain direction. Rubber duck antennas sacrifice efficiency for convenience. External antennas they significantly improve performance. So yeah, rubber duck antennas, especially if you get inside of a vehicle, inside of a house or something like that, depending on your proximity to a repeater, they really do compromise. They're not really good resonant antennas. I've heard some old Elmers of mine refer to them as good dummy loads, so they don't radiate all that well. Usually something metal is always going to be better. So one of the things I did when I first started in amateur radio, all I had was an HT. I had one of the Radio Shack HTX202s, and in fact, it's been so long ago they called them Realistic instead of Radio Shack. It was one of their brand names, and I would use that thing indoors as a base radio as well, because even with the 5-watt output of the HT, I could get into repeaters in my area. But it made it a lot better when I put some kind of external antenna outside. And one of the things I found was Radio Shack actually sold a BNC style telescopic antenna that you could put on this radio, and I took and measured and marked the resonant length for 2 meter frequencies, and I would extend this antenna out, and I noticed it performed a lot better. And I also had some like mag mounts and base mounts and stuff that I could connect that thing to, and it did a whole lot better. One little trick I did, I had a antenna mount that you could roll up the window of your car. It sat over top of the window. You roll the window of the car up, and then you ran the cable inside the window, and it gave you an outside antenna. And even the rubber duck out there was better than trying to operate it inside the car. But the metal antenna was a significantly noticeable improvement over top of that rubber duck antenna in either situation. Number 6, a half-wave dipole radiates strongest broadside or perpendicular to the wire with nulls off the ends. So keeping that theory in mind, if you had the space to do it, and I used to have plenty of space, and I had a fan dipole, and basically that fan dipole, I had resonant lengths of wire for each one of the bands that I wanted to operate. Most of them anyway. Sometimes you can, some bands, what's a half wave on one, maybe a full wave on another, but that's a whole other subject. But if you had the space to do it, if you could turn a dipole antenna going north and south, then broadside of that antenna, you would get better signal north and south as opposed to off the ends. And if you had one that you could turn east and west, even if it's the exact same style antenna, or if you had some way And there are some out there, rotatable dipoles. They make for different bands. And as a matter of fact, the hex beam that I have, it does 20 through 6 meters through 20, but there's an option to add a 40 meter element on it, but it's not an actual beam element. It's just a dipole that's attaches to this antenna and rotates. So you can rotate that dipole and get better signal one direction or another. That's probably a little more practical, but if you had the space and you could put 2 dipoles up, if you're just running a 100-watt radio to begin with and you're tuning up a G5 RV, whether you build it or you buy it, if you get 2 of them, if you make 2 of them and you can run one north to south and one east to west and put them on a switch box, then you've got you can pick up an advantage depending on where you're trying to work. All right, so let's look at for the T9B section, feed lines and connectors. So 50 ohms is the standard impedance for amateur radio coax. All equipment is designed around this value. You can get away with on HF bands running 75 ohm like TV coax. It's kind of difficult to work with because of the connectors, but they do make adapters. So depending on what kind of setup you're running. But the 50 ohm coax is, of course, going to be better and a lot more efficient. And this is a must-have when you start getting up in the higher bands, the 2 meter bands, the higher frequencies, lower band number. It's going to be a must-have. I've experimented with using 75 ohm coax back in the days when I was only running barefoot power, and it did okay, and it was kind of a noticeable little bit of a difference, I thought, anyway, at least on the setup that I had. And part of that was probably because I was using dipole antennas and such that were cut for a resonant length that were 50 ohms at their feed point. But there is some use. It won't. The 75 ohm stuff, the TV cable, is not really designed though for handling the power running through it like a 50 ohm coax would handle on amateur bands. It does come in handy though if you've got any laying around. I know a lot of folks have just went to streaming on their TV, and there's cable probably running around your house if you've got an older home that you could probably scarf that cable or just attach to it. But if you get into HF and you have receive-only antennas, then that's as good as anything else because you're just using it to receive on. But the 50 ohm coax is going to be the more ideal things. The coax cable loss increases with frequency, so you use lower loss cable for VHF, UHF, and that kind of goes along with what I was saying a minute ago. You keep running short. So the HF frequencies, the coax doesn't experience as much loss. One of the reasons that you might want to run higher quality, bigger round coax like LMR 400 on HF, and that's what I do. The reason I do that is the power handling capabilities. So if you're just running a 100-watt setup, mini 8 cable, something like that is fine. It's convenient, especially if you're running like a field operation, field day, something like that. Summit's on the air, parks on the air, something like that too. It's just a lot easier to carry and pack up and all that kind of stuff. But for your home setup, if you're going, even if you don't have the capability right now to run any kind of power, if you think you're going to be in the hobby to the point where you're going to want to add an amplifier to your station, to your HF station, then try to go ahead and start now and getting the better quality cable. And that also includes the connectors. The connectors, any kind of adapters, anything like that. Get the high quality stuff that's going to handle power. You can buy some cheap stuff out there, and if you run power through it, even the PL259 connectors, and you run power through it, it can cause a mess. When you get up into the 2 meter, 70 centimeter range, though, especially on a long run, if you've got a tower out in the middle of the field or something like that, then the LMR 400 style cable or the 213 or something like that is going to be much better, a lot less loss. And any time that you can, though, try to keep the run short. You might even have an advantage over a shorter run antenna feed line close to your house when it comes to VHF and UHF than you would having an antenna up on a high tower somewhere out in the middle of a field where you got to run 200 or 300 feet of cable, especially if you're going to run high loss cable. You may be better off just cutting a short run and putting that antenna closer to your house. SWR measures how well your antenna system matches the feed line. So 1-to-1 is perfect, and under 2-to-1 is acceptable. Under 2-to-1, under 3-to-1 actually, anything 3-to-1 or under for most radios. These solid state radios these days will fold the power back, as we mentioned in other sections. But if you want to keep it around 2-to-1 or less, that's obviously going to be a lot better. If you start getting near the thresholds of what these radios can handle, they do run a little bit hot and could potentially cause damage, even though the radio's folding the power back. It's not impossible to make a radio damage itself. So monitor your SWR. Most of your 2-meter mobile radios that we use for base radios, which is a fairly common thing, do not have an SWR meter on them. So invest in a good SWR meter if you can swing it. And some of these things now these days are priced way cheaper and they're just way more easily available. But antenna analyzers are great. You can get an antenna analyzer, and I have one, that will run all the way from below 1 megahertz, below the 160 meter band, all the way up through the 70 centimeter band. And then you can check everything. You'll be able to check everything. Any mobile installs you do, anything like that, if there's a problem, if the radio starts performing a little wacky and doesn't do what it once did, the first thing I would go to is that analyzer and connect that antenna up and check and make sure everything's okay. An antenna tuner matches impedance at the transceiver. It does not reduce feed line losses. So yeah, that's basically what it's doing, is it's tricking the radio into thinking that it's seeing that 50 ohms. Ideally, a tuner or a matcher should be used to just compensate some fairly small discrepancies. If you've got 10-to-1 plus SWR and you use a tuner or a matcher to bring it down to an acceptable level, then you are severely compromising. That is something, though, that you can easily do with a 100-watt radio, with your standard 100-watt, 200-watt radio. Even with a lot of automatic antenna, the tuners will make a bad antenna into what looks like a good antenna to the radio. You can even buy these beefed up, powerful, like the Palstar HF Auto, or even this Flex Tuner Genius that I've got right here will match a 10-to-1 ratio. But you do run into a lot of problems. You're not really radiating all that great, if at all. And if you throw an amplifier in the system, sometimes it might tune it up, but it won't stay that way if it's that far out. You can do a lot with 100 watts in a wire, but when you start throwing power in there and start dealing with things like that, then that's when you really start to notice the inefficiency in the system. So the ideal thing is to, depending on the space you have or whatever else, try to get your antennas as close to resonant as possible. I know there's going to be situations where you don't have the room and you're going to try to tune your 40 on 20 and that works pretty good or whatever. But like, for instance, my setup, I have the hex beam, which covers me 6 all the way through 20. No problem whatsoever. I don't even need the tuner. I bypass the tuner on that. I've got a 80 meter inverted L and a 160 meter inverted L. The only thing I'm really tuning right at the moment is 40. And I use that 160. It doesn't like the 80. But I'm going to put up a resonant 40 as well, because I'm running an amp and I really need that. And it's going to perform a whole lot better, because sometimes it doesn't matter how much power you throw at something. If it's not radiating efficiently, then it's not doing you any good. So just try to keep that in mind if you really want to run a good, efficient system and you're trying to work some DX and work through pile-ups or whatever else, is get that antenna as close as you can and use that tuner just to compensate when you start getting a little bit away from the frequency that you cut that for, but you're still in or close to that same band. PL259 connectors work for HF and VHF. Use type N for frequencies above 400 megahertz. Not all radios that run above 400 megahertz have those type N connectors. Some do. The Kenwood TS2000, the Yaesu FT847. I'm fairly certain on the 2000. I may be wrong. I had one, and now I'm second guessing myself. But there are radios out there that will put the N connectors. If they are exclusively UHF radios, they may have the N connectors. Most of them have PL259s. Antennas the same way. You can get an antenna for the 70 centimeter band, and most of them are going to come with PL259s. But I have purchased them before, single band antennas, and they have the N type connector on the antenna end. So it's possible you can put the N on one end and the 259 on the other, or you can use an adapter or something like that. But if you can get N type connectors on both ends, then that's the ideal thing. But it's not always practical to do that. PL259s are going to be probably the most popular. They are referred to as UHF connectors, but they're really anything but. I'm not sure how they got that name, but it's fairly common to see them packaged that way. But the true UHF connector, what works good on UHF, is the type N. The 70 centimeter band, you're probably not going to run into a whole lot of problems with it, but I think if you start working above that band, and I never have, so I don't know for sure, I'm sort of speculating here, but if you start working above the 70 centimeter band, then that type N connection versus a 259 may be a little more important. And then all outdoor connectors need weather protection. Water intrusion is the number one cause of antenna system problems. Coaxial seal is your best friend. If you don't have the capability of putting all your outdoor connections other than the antennas themselves in a box or something like that, depending on what you're running, coaxial seal on anything that's outdoors. All the antenna connections are going to be outdoors. If you run PL259s or 50 ohm coax out to your antennas, they're going to be outdoor connections. So get some kind of seal put around that thing and protect that connector and that coax as well. I'm kind of fortunate on where my antennas come into the house because I have a carport next to my shack, so I'm able to kind of shield everything that comes in there. But all my antennas, of course, are outdoors, and all those connections need to be shielded and protected. So that is section T9 and the summary of that. So we will be going to the final section, and that will be, it's actually T0 instead of T10. So if you, whenever you're looking for that section, if it somehow gets grouped at the top as opposed to the bottom, T0 is the final section.